Hey everyone! So we've talked about ocean circulation, we've talked about surface circulations, and a bit about the thermohaline circulation, so that kind of deep water sort of movement. But we haven't really quite yet talked about what happens when the waves approach the shore. So that's what I wanted to kind of focus these next couple lessons on. So when we think about waves, we can determine types of waves in kind of two ways, how they are created and how they are restored, basically. So what you might be familiar with are wind waves, common wind waves, right? If you've been like driving across the Bay Bridge and then you've seen that the bay is moving, that water is moving because of the wind. Then we also have storm waves, have likely heard of this term tsunami, and then also tide waves. And what we're looking at here is wave period in seconds and the abundance and energy of wave types on our y-axis. So these larger waves, quote unquote larger waves, have much longer periods than like those smaller waves. And when we talk about waves in general, we kind of classify them in terms of either deep water waves, intermediate, or shallow water waves. And how we classify those is simple math. But essentially, and how if the movement is being felt by the bottom of the ocean. So what we can see here on the right-hand side is this sort of little orbital motion that's going down the water column, and you can see that that is getting smaller and smaller. So that's indicating, and then it's gone. So then that's indicating that there's no wave motion being felt at these deeper levels. And then as these waves approach the shore, then they start to feel the bottom of the ocean. And then, so this would be our intermediate, and then we have our shallow water waves here. So we determine that a deep water wave is where the depth is greater than or equal to the half of the wavelength, basically. And then a shallow water wave is where the depth of the energy is less than 1/20th of the wavelength. And we can determine the speed by the square root of the gravity times the depth. So as waves approach the shore, they actually slow down in speed, and they can also get taller, and the wavelengths get shorter as well. And you can see that really nicely in this diagram. Yeah, so as they approach the shore, they transition from deep water to shallow water waves. And how they come onto the shore is another process we're going to talk about. The first is refraction. So as the waves come into the land, they can be kind of refracted away, or the energy is refracted out. In this little bay indentation here, these yellow lines, or yellow arrows, infer this wave energy. And you can see in this bay indentation how the lines kind of curve out a little bit. That's implying that the energy is kind of also curving around that bay region. And then if we were to look at the ocean bottom underneath, you can see that there's almost like this little wave created by the bottom of the ocean as well. So that's kind of helping draw that energy into the sides. And then alternatively, we also have headlands. So then there's more energy that's felt and concentrated at the tip of the headland than in a way, bay indentations further away. And here's just a kind of a picture showing some wave refraction on an embayment. So there's less energy being felt kind of right where the waves are coming onto the beach, as opposed to these little kind of minor headlands, for lack of a better word. But there's not always a beach, right? That's not always the case everywhere. So we can have wave reflection as well. So as the wave approaches the shore at an angle, it hits the coast and then is reflected away from the coast at the same angle. We also have wave diffraction. So this is when the energy is then spread out sideways to the direction of the wave travel as it approaches the shore. So we'll talk about this term breakwater here in a little bit, but essentially, as you can see here, you can think of it as like a row of rocks, basically, that are put there generally by humans, and you can see how the energy is then kind of crescenting out, and then we have how the waves interact with each other, and they are creating these little kind of square waves, which are kind of interesting. So you may have noticed how on different beaches the waves break at different points, or maybe the waves have different sizes, and that is another thanks to the bottom of the ocean and how the waves, the energy is interacting with the bottom of the ocean. So essentially what we have here is as the wave base starts to interact, right, the velocity decreases, so the speed decreases and the height increases, and the wave steepness is defined as the height over the length. And then once that steepness is greater than or equal to the ratio of 1/7, then that wave starts to kind of topple over and break. And the shape of the shoreline is really what affects the way that waves break, which is kind of interesting a little bit, right? So the really, really steep beach slopes gives us these surging breakers, so these really, really tall waves. Whereas if you have these moderately steep beach slopes, then the tunnel can then collapse, which we call plunging breakers. And then if it's a really, really, really gentle beach slope, then it just kind of like comes up onto the shore and comes back. Foam slips down the face of the wave. So next time you go to the beach, maybe try and determine what kind of waves you have there. And then here's just some pretty pictures of some waves. So these are spilling breakers. This is a plunging breakers, is generally where you would see surfers. And then we have a surging breaker, and I'm very well convinced that this photo is purely perspective. Like someone was just taking a little, taking a camera right next to the edge here. But it gives you a sense of what a surging breaker would look like. And you're also probably familiar with something called a rip current. So this is a really, really super dangerous part of the shoreline. It's this region of seaward return flow that is really narrow, and they can be some distance apart. So you can see in this photo here how there's like these little lines basically, but they're a bit apart, right? So what happens is they have to be swift enough in order to carry enough water beyond the surf zone. And these are super dangerous. If you're ever caught in one, you need to swim parallel to the beach and then to shore. Mother Nature is scary, and she does not care about you at all, and she will drag you out. And what happens basically is you get you don't realize that you're being dragged out really. And then you try and swim back in, but you're going against this current that's actively pulling you out. So folks tend to get really tired really quickly and then drown. So super, super dangerous. You'll likely see signs along beaches to say, be cautious of these. And then the last major wave I wanted to touch on in this lesson are tsunamis. So I want you to think for a moment if you believe that a tsunami is a deep water wave or a shallow water wave. So take a second, think about it, remembering our definitions of what a deep water wave and a shallow water wave is. And it turns out that tsunamis are actually shallow water waves because they have a super, super long wavelength and a really long period, but they also travel insanely fast. And it depends on the water depth. In the deeper waters, they travel much faster, but they tend to travel around the speed of a jet. And the wave height is actually pretty crazy. In the open ocean, It can be as much as several meters, but again, it's spread out over a super, super long wavelength. And then the closer they get to shore, right, they start to interact. Well, as they approach the shore, kind of the water goes out. The water right at the shore goes out, and then that makes the wave much, much taller. If you've ever seen any of the videos from the 2011 Japan tsunami, there are some videos of these fishermen boats offshore, and it's kind of eerie, but you can see how they kind of go up and down, but then once it approaches the shore, then it's actually pretty terrifying. So I will also post this video on iLearn for y'all to watch. It's quite nice. So what do tsunamis look like when they come onto shore? Well, they're moderately terrifying, in my opinion. So if you're close to the shoreline, then you may not even realize that it's happening. It just kind of looks like a normal beach time, right? And then as time goes on, then the tsunami itself, the wave comes onto shore and pretty much destroys everything in its path. And what's the danger of this, of course, obviously the water coming in is really dangerous, but also the water leaves eventually as well. And that retreat of water takes debris with it, which can be, not great. So this is in Thailand, I believe 2008, I want to say. And then this was the 2004 tsunami in India. So you can see before and after, very, very stark differences in several things, really. I mean, it's obviously much more brown on this end, indicating that everything kind of got pulled out. And even the shore itself is pretty drastically changed. Okay, so those are how waves approach the shore. And then we'll talk further about some other types of waves coming up. Thank you for listening.